My name is Wei Chen. I'm a researcher from Microsoft Research. And this is a joint work with Tianlin, Zihan Tan, Mingfei Zhao, and Xuren Zhou, who were all my interns or visiting students before. Now they all went to different ways in graduate school or find a job. So I'm the one stuck in here giving the talk. So let's start. So for motivation, I guess for this community, I don't need to give another fancy network picture to show what it is about. So it's about influence maximization. Influence maximization is a basic task that, given a network, selecting a number of nodes, usually a small number of nodes, so that you can maximize their influence coverage. And I will give a motivating example for people who are not familiar with this optimization task. It has applications in viral marketing, in outbreak detection, or rumor monitoring, or control the rumor spread, and so on. So in this talk, and we consider the robustness. And I'll also motivate what does robustness exactly mean, basically how it handles uncertainty. So consider this fictitious network. And we have a number of nodes representing individuals and edges representing their relationships. And a company trying to promote some product in this network. And the company rely on the influence cascade or information cascade in the network. So this cascade can be modeled in different ways. There's a classical model called independent cascade model, which works roughly as follows. So every edge has a probability. Actually, here it shows like undirected, but it could be directed. So, and this we call influence probability. And all the probability forms a vector we call theta. It's a parameters vector. And in one cascade, it starts with, say, some seeds. Say I select this couple of seeds. And the seed will try to influence their friend or neighbor in the network. And the probability of successful influence is given by this probability, say 0.7 here. So you basically flip a coin, and if it's successful, you influence your neighbor. And for this instance, it's not successful. It's dashed gray edges. And then in one step, you already the two seeds already influence these nodes, but you can continue recursively, like in the second step, this node further activate one more node. So this is one cascading process. It's going so on and so forth until no further activation happens. So, and this is an independent cascade model. And some other models follow the similar way. And the important quantity people usually look at is called influence spread. This is the expected number of nodes in the network that will be activated by this process, given the starting seed node S. So we call it sigma S. And we parameterize by the theta, the probability vector. And Kempe et al. In 2003, in this very conference, KDD, they proposed this influence maximization problem. Is basically given this graph and the parameters, how to find k nodes in the network so that you can maximize the influence spread of these k nodes. We call seed nodes. And there's a lot of study on how to do this algorithmically. And there's a lot of improvement, too, including Jennifer Christian, our keynote speaker this morning, who has a very good near linear time algorithm, and also some follow-up improvement. So, but we are not focused on greedy algorithm itself. But to give you a very brief introduction, the greedy algorithm is basically you select one node at a time. You select first node with the largest influence by itself. You put it into the seed. And then you select the second node, which marginally has the largest marginal seed, given you already select the first node. And you put the second node into the seed. And then you select the third and fourth, so on, until you select k nodes. So that's the greedy algorithm. And it's been proven it's achieved 1 minus 1 over e minus some small epsilon approximation. So that's the story so far people already studied. Now, what is the robustness. It's related to a question people often ask. So when I give lectures on this topic, many people ask, what are the probabilities? Where are they come from? How can you tell me this probability is 0.2 or the other is 0.4 and so on? So actually, no one knows this probability, right? So it's studied from data. There's a number of other studies. They learn the actual Cascade data, actual action traces, who did some action and who followed that, did another action, and then they learn the Cascade data. But even when you get Cascade data, what you really have is you don't recover ground truth. No one knows the ground truth. What you have is actually maybe more realistically, you should think it as an interval. Like with some confidence, you know that, oh, this edge maybe 0.2. I don't know, it's really 0.2. Maybe it's between 0.05 to 0.35. It's a range with some confidence. So that's maybe more realistic. So no one knows the truth, actually. So now the question we want to address is, suppose what you have is not the ground truth, which no one knows, but this kind of intervals. We can call it interval graph or interval space. What can we do about influence maximization? So this is a robust influence maximization I'm going to address here. So again, to try to put it in a more technical sense, so remember before we have a single value. Now we change it into an interval for every edge. Every edge has an interval showing the kind of the possible range of the values on this edge. And one thing is we do not make further assumptions for this interval, within this interval, whether it's uniform distribution and any distribution. Any distribution goes. But it's just input as an interval. Now, given this graph where edges have intervals, so how do we talk about some kind of robustness? So this is our way. We define it called a robust ratio. And first, we have this parameter space. It's basically a cross product of intervals of every edge. And based on this big theta, the space, we define this robust ratio. In the numerator, suppose S is a given solution. Suppose S is what you find. And then S has an influence spread given one parameter, particular parameter in this space. But this one usually is smaller than the optimal solution. S theta star is the optimal solution in this given parameter theta. So this is usually less than one value. But you have a lot of different thetas, actually infinite number of thetas in this big theta space. So we want to take the minimum of this value, and we call this robust ratio. Conceptually, it just means that if you have some S, you're not sure which one is the real ground truth, you want to provide the minimum guarantee. And this is the minimum guarantee in terms of the influence spread you give versus the best influence spread. So this is basically a worst case philosophy. Now, given this ratio, how to define the robust influence maximization, then it naturally follows basically the input now is the graph plus the interval space. Then you find k node in the graph to maximize the robust ratio. So basically, this maximization is trying to maximize the worst case value. So you know it could be very worse, but you want to maximize the worst case value by giving a proper seed set. And this follows the robust optimization approach, usually used in operation research. Now, a standard theorem usually given in this context is NP hard. So this problem is, of course, NP hard, because even you reduce this interval space to a single value, like you really know the ground truth, this corresponds to the original influence maximization question. It's already hard. And also, this ratio cannot be improved beyond 1 minus 1 over e plus epsilon. This is another hardness result. So, so the first thing we look at is, can we do something to give some guarantee? And so this is the algorithm we're trying to propose. We call LU greedy. And it's very simple, actually. So basically, we are given an interval space. And each interval has a LE and RE, call it left end value, right end value, or lower or upper value. So the greedy, you first do a greedy using a standard greedy algorithm, any state-of-the-art scalable algorithm. But you feed the greedy algorithm with left end probability, the lower, we call it lower greedy. And then you feed it with upper greedy. So you'll get two sets, possibly different sets. And then you just find the two sets with larger influence spread on the left end parameter, on the lower parameter. So this is what you output. In the graphical illustration, basically, these parameters on the edges are the left end, the lower parameters. And you do the lower greedy, find the C set. And this is the upper greedy, find another C set. And just find them to be this one. Well, one may ask, actually, in yesterday's poster session, someone already asked, so isn't this one always better than this one? Since you're doing lower greedy on this parameter, theta minus. So it seems you don't need to do the max. But mathematically, we don't have such result to show it's really better. And for some later mathematical analysis, we need to add this term. So basically, it becomes a max of two terms. Even though in our empirical evaluation, usually this one is always win out. So given this algorithm, we give a solution-dependent bound. We do have some kind of guarantee. So it's show us this theorem. Basically, the algorithm ratio can achieve. It first has a familiar term of 1 minus 1 over e. That's, again, is by greedy on some modular function. So that's a standard. And if you really know the ground truth, then it will be 1 minus 1 over e. But this alpha theta is a new term we call gap ratio, which shows the penalty on because of the robustness on the intervals. So this alpha term is basically a ratio between your solution, the low LU greedy solution on the lower end, on the left end space, the influence spread, over the upper greedy solution on the upper end parameter. So this is the ratio. And from this formula, basically, intuitively, I want to give you some idea. Basically, look at the last term here, comparing with the term in the denominator. The only difference is this is sigma minus, this is a theta plus versus theta minus. Intuitively, if the intervals are small, short, so theta minus is close to theta plus, then these two values should be close to each other. Then you'll get a better result. But of course, this is model is very complicated. It's actually nonlinear. So even if they are close, it may not be good. So that's our next theoretical study. So I will not read the theorem result. It basically says, in the worst case, the gap ratio you can achieve is actually pretty bad. The worst case in the sense, for example, taking the middle bullet. So if you have the delta is the length of the interval. If every length of interval is 1 over n, it's already very small. But for a deterministic algorithm, I can always find a graph that actually the gap ratio is log n over n, which is not good. But the catch is here is I give you a very bad graph. The social network in reality usually is not that bad. So there is a hope. But that's, we say it's maybe future work to study a particular graph. What would be the good gap ratio? So this is in general sense, and it could be very hard. And this is actually related to the stochastic block model with Erdo-Shreni graph, kind of a percolation threshold or emergence of giant component, those kind of things. You can give this result. So now how to improve this? It basically means the interval should be small. And there are two possible choices. In this paper, we explore the first choice called sampling. We try to do further sampling on edges to shrinken the interval to make the result better. And the other, we left it as a future work. Basically, for study graph structures graph structure's influence or dependency on the gap ratio. So very briefly, let me go through the sampling. Basically, with more samples by the law of large numbers, you'll have more and more confidence on the edges, so the interval should be small. Now, typically, you can do the uniform sampling where every edges are sampled same number of times. But we also want to promote a non-uniform adaptive sampling, meaning based on the previous sampling result, you can adapt your strategy. Some edges are less important, you should sample less. Some other edges, maybe you should sample more. For the uniform sampling, we give some theoretical results based on kind of concentrations on how many samples you need per edge to reach a reasonable gap ratio. But let me ignore this. For the adaptive sampling, we propose the following heuristic we call information cascade sampling. So it basically follows the idea the edges that are important should be sampled more. But what are the edges that are important? Those edges usually are on the cascade path. If you touch those edges, those are more important. So that's basically the idea. And so basically, it's an iterative case. You first use a rough interval, find some seed set. And use that, we call it SIG, and use that to do cascade, and the cascade give you more samples, and then use that more samples, you do an update on the interval. You should have a little bit shorter interval, and use that shorter interval to do greedy again, then that gives you a different seed set, and just move so on. And so this is a quick illustration. Basically, the first iteration, you find this as a seed, then those red edges are positive samples, and those zero or gray dashes are negative samples. Then you get better understanding about the edges. And then you update your interval and try another seed, you give you other samples. And then we use this particular updating rule, which adopted by a recent paper on the related to confidence interval. And we use this rule to do update. So one more comment is this is has some resemblance to multi-unbanded kind of learning scheme. Although for this work, we didn't provide a theoretical analysis. It still stays as a heuristic. So for empirical evaluation, we look at several networks, in 3 networks. The first one is a collaboration network of archive. The next 2 are Flixer topic-aware kind of network is drawn from movie rating. This is actually thanks to the researcher who did this work. We got the data from their study. And the good thing is their study, actually, the probability are learned from actual action trace. So it's not a synthetic one. And based on that, the learned probability, we give a rough estimate on how many samples are used for each edge, and then we derive an interval. Use that as an interval to start with. And this is a first study. We try to look at the x-axis is the interval width, like whether the interval width is short and large, how it affects the gap ratio. And here we also use an alpha bar. We give an estimate of upper bound, but this estimate is still not close to the lower bound. But it shows a general trend, like the curve with same color is one is a lower bound, the other is upper bound. And the general trend is clear. Basically, when the interval is getting larger, you have a quick drop in your quality. So you should put the interval quite tight, like below 0.05. That will give you roughly alpha value 0.6 or 0.7. So reasonably OK performance by our theoretical results. The next, we look at the different sampling algorithms, compare uniform sampling, our information cascade, adaptive sampling, and other baselines, outgoing edge only sampling. I only sample outgoing edges immediately from the seed node. Do not do the further cascade. The outgoing edge baseline is pretty bad. The black lines are always at the bottom, but the others are OK. And information cascade, the blue one usually has a slightly better performance. So there are a lot of related work on influence maximization, like people did how to learn the probabilities and how to do scalable algorithm. And He and Kempe, they have a work on how to address uncertainty, but that's a different optimization problem. And Cross et al. Do a general robust optimization framework for submodular functions. And in the next talk, which you're going to hear in a minute, He and Kempe, they study the same problem, but the objective function is the same, but the approach is quite different. So you can see two different orthogonal approach on this. They use by criteria approach, and they work on finite number of possible choices, while we work on intervals. So you'll hear from He next. So as a conclusion, we propose this rim problem to handle data uncertainty. We propose the LU greedy algorithm, and we propose some adaptive sampling method, hopefully to handle uncertainty. And of course, there is a lot of future work, like the upper bound. It's not tied. I don't know how to move it for a given graph, and how to provide confidence interval. Like yesterday, also some people asked, for maximum likelihood, it's not easy to provide a confidence interval. And also, in general, I feel that this is still show a big data challenge. Basically, for influence study, the data is still not large enough. It's still hard to get accurate estimate of influence between pair of people. And given this constraint, how to do better sampling, model learning, and algorithm design, that's need a lot of joint effort from the community. So thank you.
Thank you so much. We have time for some quick questions.
You gave a method in which you didn't prove, in which you sampled more of the edges along the path that lands up being used. How hard do you think it would be to prove something along those lines? And have you tried to think of any counterexamples which would tell you what the conditions of such a theorem would have to be?
Thank you. So very good question. So for the sampling method, we didn't try very hard. But we have another independent work trying to apply multi-unbounded to influence maximization. We already have the first result, and we're doing an improved result now. But the key difference is that objective is not robust objective. So it doesn't involve an interval that you look at worst case in the interval. I think that part make the analysis could be much harder. So we are in the process that we're not considering this part, but then we combine with multi-unbounded.
The part that makes this harder, which is that you have an interval, one might try to think about, are there things that you could put in which would make that interval act in a strange way, or do you believe that under very general circumstances this would work? And maybe we should follow up on this offline, but anyway, I would be trying to think about what are the conditions of the theorem under which you might get something like you get with a multi-arm bandit. So,
Thank you.
Yeah.
Thank you. Yeah, so we can talk it offline.
You have a quick question?
So, may I ask about the objective you considered to maximize? So you consider the ratio between the influence spread the algorithm provide and the influence spread of the optimal seed set.
Yeah.
Is it important for practical tasks to maximize this ratio, or because the question is because naively I would suggest that it is more important to maximize the minimum of the influence spread, but not the minimum of the ratio. Am I right or not? And if I'm right, then what can you suggest? What could be the hypothesis of an optimal, a good algorithm for the other objective I suggest?
Okay. If I understand correctly, you're saying instead of optimizing that ratio, just optimizing the influence spread, like the one in the numerator.
So just to guarantee.
For that problem, actually for IC model is easy, because IC model has a monotone property on the theta parameter. If you want to maximize the minimum of that one, you just maximize the left end parameter. You just maximize sigma theta minus s. So if that's what you want, yeah.
So do you think that a simple greedy algorithm will be something well motivated and
Simple greedy algorithm?
simple greedy algorithm? Yeah.
Let me quickly go to that. Yeah, I'm saying that if you, instead of maximizing ratio, just maximizing this one.
Yeah.
This one, oops, why? Sorry.
Yeah.
So this one is monotone with respect to theta. So mean theta of this numerator is just theta minus. It's a parameter of theta minus. So it's
Yeah. Reasonable. Yeah.
It's yeah. Maybe we can discuss offline. I mean,
Thank
it's
you.
different objective. Thank you.
Thank you. I believe I see the answer.